Let's look at another example and notice that the one I've written here is not separable. So we would not be able to use separation of variables to solve this, but we'll see that our new technique of assuming that our solution can be expressed as a power series will still work on this. So if I assume that my solution is a power series or has a power series representation centered at 0, again, motivated by the initial condition being y of 0 equals 1, then I start off just like before with y equals a sub 0 plus a1t plus a2t squared plus a3t cubed, and so on. And also, like before, that allows me to find dy dt, and I just take the derivative of what I have in pink. So that would yield a1 plus 2a2t plus 3a3 t squared plus 4a4t cubed plus 5a5t to the fourth, etc. So this, again, doesn't change in any way. So I'll point out, as I change my differential equation, the pieces y, dy, dt, and so on, those don't change. What changes with the differential equation is how I put those pieces together. In our previous example, we simply set the pink equation equal to the blue equation. And that was because our differential equation was dy dt equals y. There's one big difference here in that we have this plus t. So when I put these two together, that means that dy dt goes on the left. That's the blue equation. So that's going to be a1 plus 2a2t plus 3a3t squared plus 4a4 t cubed plus 5a5 t to the fourth, so on, equals t plus the pink equation. So we're going to do the same thing as before, where I'm going to equate like coefficients. But one thing that's going to be really useful to do before I move on is to bring that t that we've added here into my parentheses. So collect it with the appropriate term. So this is t to the first power, and there's another t to the first power. It's right here, a1t. So we want to lump those together so that when I start to look at the coefficient of t to the first power on the right-hand side, I recognize that there's really two terms involving t to the first power. So the way that I could bring that in there is to recognize that the right-hand side is a sub 0 plus a1 plus 1 times t. And again, that's a reflection of bringing the 1 times t that I have out front into the parentheses. So if I were to distribute this t through here, I'd have a1t, which is here, and I'd have 1t, which is here. The rest of these terms are unaffected because their powers of t are different than what was added to the set of parentheses. So when I now start to equate like terms, I'm going to take this equation on the left and equate it to the one I've written here. So to begin with, I can use my initial condition. Again, here we're told y of 0 is 1. So same thing, I go back up to my equation y here, and I plug in 0 for t. That leaves only a sub 0, so that must equal 1. Then we have equating the coefficients. I'm going to have that the constant terms on both sides must be equal. So for this, that means a1 is equal to a sub 0, and we know a sub 0 is 1, so we get a1 is 1. Then I want to take the coefficient of t on both sides, and this is where we have to be careful. I already was careful in making that, rewriting that second line. So by looking at what we have there, in this part I have 2a2 on the left-hand side is equal to a1 plus 1. And again, the part that might be easy to overlook is the plus 1 that's really coming from that additive t that we have there. Now, 2a2 equals a1 plus 1, but a1 plus 1 is 2. So this gives us a2 equals 1. Then I have looking at my next grouping here, if we were to group together the coefficient of t squared, we're going to get 3a3 equals a2. So a3 is 1 over 3. Then if we look at the next set of terms, we'd get 4a4 has to equal a3. Which means that a4 is 1 over 3 times 4. We would likewise get then 5a5 is equal to a4. So a5 is 1 over 3 times 4 times 5. What I can do at this point is take advantage of the pattern looking very familiar to what I had in the last example. And we've already established that if I have almost a factorial here, the only part missing is the times 2, that I can write that with a factorial as long as I put a 2 in the numerator. So we get this kind of pattern, and we get this here. Now, the problem is the pattern doesn't apply to these first two terms. 2 over 1 factorial and 2 over 0 factorial should be 2, not 1. So this one is a little bit harder. It doesn't always end up that you get one that's immediately recognizable as a Taylor series like we did in our previous example. So the theme here of this particular video is finding the appropriate function. We might have to do a little bit of work. So what we're finding here is that a sub k is equal to 2 over k factorial as long as k is 2 or greater. So again, we're assuming that our solution function is y equals the sum from k equals 0 to infinity of a sub k times t to the k. So what we're finding here is that I have a pattern, but it only works for k equals 2 or greater. Of course, you can write the power series by siphoning off a few terms. So this would be allowable. And we found that a0 is 1. We found that a1 is 1. And then for the sigma notation, at this point I can put in 2 over k factorial times t to the k. So of course this is our solution, but we're really not done. We'd like to end up with a very clearly defined function of t. Importantly, not written in sigma notation. So if I were to encounter this and then be asked to find the sum here in terms of t, what I'm most drawn to is yet again this part, the fact that this is close to a Taylor series. So if I were to guess what function this would be, I would first be drawn to the fact that it looks like 2e to the t, right? And of course, it's not exactly equal to 2e to the t. So what we can think of here is that if I guessed 2e to the t, we could adjust our guess. So it almost looks like 2e to the t. If you were to write out the terms of 2e to the t, you would get 2 plus 2t plus 2t squared over 2 factorial plus 2t cubed over 3 factorial, and so on. And of course, if we go back to our coefficients, here's 2 over 2 factorial, 2 over 3 factorial. Everything's going to match here after this point. So the part after this dotted line matches. So what that means is that my guess here is very, very close to what I have above. So if I wanted to go from this guess to what I have here, notice that my current guess is a little too large. It's got a 2 and a 2t, where I want a 1 and a 1t. So what I can do is then subtract 1 and subtract t to take it from here to what this is. So if I subtract 1 and I subtract t from the right-hand side to get the sum I already have here, then the sum of that should be the same thing as the left-hand side, minus 1 and minus t. So our solution is y equals 2e to the t minus 1 minus t. So my process there, again, was very similar in the same as the example as before, except, like I said, I noticed a few of my terms are off, and if a few of the terms don't match, but after a certain point all of them do, then you can accomplish finding the function by adjusting the first several terms. Do I need to add or subtract a constant, t to the first power, and so on? And here you can check, now that we have this, if I then take the derivative of 2e to the t minus 1 minus t, then we'll get t plus the function we started with there. And of course, it satisfies my initial condition as well. So when you're going through this process, the best case scenario is you immediately see exactly a Taylor series that you're familiar with. The worst case, well, not the worst case, the next best case is that you can still look at that and see a familiar Taylor series, but maybe have to do a few adjustments to that starting point. So think about it as kind of getting a guess that's very close and then tweaking it as much as you need to get to what you actually see in your sum.